Welcome to Lesson 12A, Oblique Shock Example Problems. In this lesson, I'll do two example problems for oblique shocks. Now let's go back to the 2D wedge case and do an example. Here we have air flowing at supersonic speed into a two-dimensional wedge. Oblique shocks form. We give the pressure, the temperature, delta, the wedge half angle, and upstream Mach number. We label regions 1 and 2 before and after the shock. We want to calculate shock angle, P2 and T2 and M2. We make our usual A and A, steady, ideal gas, adiabatic, and we ignore boundary layer effects along the walls. There will be a boundary layer building up along this wall, which will have a displacement effect that makes this wedge appear to the flow as a little bit thicker, so theta will not be exactly delta, but a little bit bigger than delta. But we're ignoring such viscous effects of the boundary layer, so we'll let theta equal delta, or 20.0 degrees. Now we use the theta+beta+M equation to calculate beta. This has to be done implicitly, since you can't solve for beta explicitly from the theta+beta+M equation. You can use the false position method, Newton's method, trial and error, however you want to solve for it. Or you can just use the CAC online calculator. I get beta equal 37.76 degrees for the weak case. Now we can calculate M1N, which is M1 sine beta. I get M1N as 1.837. Now we use M1N in our normal shock equations in place of M1. For example, this is the equation for pressure ratio, but I've replaced M1 with M1N. I get 3.77. And I can use ratios to get P2, where P1 was given, so I get P2 is 382.1 kPa. Now we solve for M2N, using the same equation we had for a normal shock, but again everywhere we have an M1, we replace with M1N, and we solve for M2N rather than M2. I get 0.60839, and report it to 3 digits as 0.608. Similarly to pressure, we calculate temperature T2 as T2 over T1 times T1, where we use the T2 over T1 ratio for a normal shock. Again using M1N and M2N. Leaving out the algebra, I get T2 equal 449.2 K. So we've calculated beta, P2, T2. Now we need Mach number M2. Well, M2N is M2 sine beta minus theta, which we can solve for M2. And plug in our values. I get M2 as 1.994. Again, it should not alarm us that M2 is supersonic, especially for the weak oblique shock case. Now we'll repeat for the strong oblique shock case. If you're solving the theta+beta+M equation for the strong case, if you're using an iterative method, such as false position method, you pick your first guesses with a large beta, for example 80 degrees, to ensure that you get the strong case. Here's a summary of my results for the strong oblique shock case. Beta, M1N, M2N, M2. Notice that this is subsonic, since this is a stronger shock. P2 turns out to be 1027 kPa, or 10.14 atmospheres. This is much higher than the weak case, as we might expect. Finally, T2, which again is much higher than the weak case. I'll do one more example. This is exactly the same problem as the previous one, except I have a bigger wedge half angle. It was 20 degrees in our previous problem. Well, this one turns out to be a lot simpler, because my theta+beta+M plot at Mach number 3 turns out to have a theta max of about 34 degrees. Well, our delta is greater than theta max, so this tells us that an oblique shock is not possible for this case.
But sir, there has to be a solution. What if you set this up in a wind tunnel? What would happen?
Well, Boris, this is a case where instead a bow shock will form.
And this is what our flow will look like.
Oh, cheerio.
We can calculate pressures, etc. across this normal part of the shock. And if we knew the shape of this bow shock, we could locally calculate all the properties downstream of the shock, but we're not going to do that here.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.
That's all there is to it.